Hello, Luke. Welcome to Lesson 22. All right, today we're talking about expressions and conditional equations. This is going to be the basis for a lot of problems that we're going to have throughout the year. So this is an important lesson today. So to begin with, let's start talking about expressions. Everything that we've been doing up to this point, at least in large part, has been dealing with expressions. So when we think of expressions, things like this should come to mind. So like 3x plus 2y plus 6z. That would be an expression. A simpler expression might even be 3 times 2 plus 1 plus 6. Or if we wanted to add some parentheses in there, we might say that an expression would be 3 times 4 plus 2 minus 5 plus 6 times a negative 3. All right. All of these are expressions. And this is really what we've been doing all along. We've been taking these expressions and we've been simplifying them, trying to compute all of the addition and subtraction and multiplication that needs to be done in an expression such as this or such as this. Here, we might be taking this expression and evaluating it, saying that, well, what is it going to be if x is 1 and y is 2 and z is a negative 1? What would this expression simplify to? So we've been trying to take these expressions and find the value for the expression. So every expression is just a lengthy, detailed way of expressing a single value. So if we take, this expression number 1 and we plug in our values here, let's just do that real quick. So we would have 3 times the 1, because that's what x is, plus a 2 times a y, which is a 2 as well, plus a 6 times a z, which is a negative 1. We're plugging all that in. We get this new expression, and then we're going to simplify that even further by multiplying things out, right? And then we simplify even further by combining these things. So 3 plus 4 is 7, 7 minus 6 is 1, and we end up with a value, right? So this is the value for this expression, given that x is 1, y is 2, and z is equal to a negative 1. All right, so we have an expression and we have a value for that expression. This whole detailed thing is just a really messy and complex way of writing the number 1. All right, this next one is very similar. So if we have 3 times 2 plus 1 plus 6, and we want to simplify that, we'd start with our multiplication, because of course we know our order of operations tells us multiplication has to be done first. So we'd go 3 times 2, which is going to be a 6, and then we have, in addition to that, a plus a 1 and a plus 6. Adding that up, we get 13. So this expression, this number 2 expression here, that is just another way of writing 13. It's a complicated way, but it's another way of writing 13. That's the value. The value of this expression is 13. And then finally, we have this one here, which I think you get the idea, but just doing it quickly, we could see that you do our parentheses first. 4 plus 2 is 6. 6 minus 5 is 1. So we have a 3 times the 1 in the parentheses plus the 6 times a negative 3. Multiplying this out, we'd get a 3 plus a negative 18. And then a 3 plus a negative 18 is, of course, a negative 15. So this number 3 is going to be just a complicated way of expressing this value, negative 15. All right? Now, in algebra, it becomes very important to move past expressions. We want to actually start comparing expressions. So let's say we have 2 expressions. Let's say we have, let's just make one up here. Let's say we've got a 2 times a 3 plus a 10 minus a 6. All right, and then we have another expression. Maybe we'll do this in a different color. We've got maybe a 4 plus 3 times a negative 6 plus 2. Okay, so these are two expressions. They both have a value. They're expressing a value. Now, we could figure that value out, but just glancing at them, you probably don't know right away what that value is for each expression. And they're probably going to be different, but we don't know. The value might be the same. So in algebra, we like to start comparing expressions. And if we compare these two expressions, we're going to come up with one of several outcomes, right? So let's think about that. If you've got these two expressions, we're comparing them, what could possibly happen? Well, you could end up saying that these two expressions are equal to each other, right? Maybe their value is the same. All right, in which case we would represent that by throwing an equal sign between them, saying that this side is equal to this side. They're the same thing. All right, we might also say that they're not equal. Maybe we compute them and they're not equal. One way to write that is to draw an equal sign with a slash through it. That would mean not equal. All right, another thing we might come up with would be to say that one is larger than the other. So maybe the value, whatever it is, of this expression is actually larger than the value of this expression. Well, then we would write that by using the greater than symbol, right? Hopefully you remember that from previous years. The greater than symbol, it's always opened towards the bigger side. All right, so let's say this value is bigger than this value. We would use this greater than symbol. On the other hand, if the first value is less than the second expression, well, then we would use the less than symbol. Okay, that would just again say that this side is less than this side. All right, so in comparing expressions, we're going to have one of these four things happen. And really, you might even say one of these three things happen, these first three, if you really want to look into it. It's really these three things that are going to happen. If they're not equal, well, then they're either one is bigger than the other or one is less than the other. So really it's these three. But sometimes it's important to specifically say that two expressions are not equal. And that's when we'd use this equal sign with the slash through it. So it's important to know what that sign means. But generally, these would be the three options that you would have for these two expressions. Okay? So real quickly, looking at these three options, we kind of divide them up into two different groups. All right? So if we're concerned with these two, if in fact one of these two is true, either this side is greater than this side or it's less than this side, we would call those expressions inequalities. So let's just say, for the sake of the argument, that, let's give these a number. It'll be a little bit easier. Let's give this expression number 1. This is expression number 2. So if it turns out that expression number 1 is actually less than expression number 2, okay, this is what we would call an inequality. And that's pretty self-explanatory. It's an inequality because they're not equal. In comes from the Latin meaning not. Equal, you can see that word right in there. So not equal. So if 1 is less than 2, well then they're an inequality. If on the other hand if expression 1 is greater than expression 2, again, it would be considered an inequality. They're not equal. All right? On the other hand, if 1 is in fact equal to expression number 2, then we would say that these two compared to each other make up an equation. An equation. All right? So these signs would indicate inequalities. The equal sign indicates an equation. And you almost see the word equal in equation. And all that means, again, is that there is an equal sign. They are equal to each other. So whenever you hear the word equation, recognize that what we're talking about are two expressions that have been set up on either side of an equal sign. So we're saying that those two expressions are equal. All right? So that is kind of the terminology here. Terminology here that we want to make sure that we're clear on. In this book, we are going to be more focused on equations than inequalities. We will touch on inequalities, and later on in Algebra 2, for example, you'll be digging much more into inequalities. But for this year, we're going to be focusing primarily on equations. So two expressions being joined with an equal sign. All right? So let's move on from there. So when we talk about equations, there are several different kinds of equations that we can reference. So let's take a look at some of these. I've laid them out, and let's just explore what some of these equations actually mean. So if we start with the first one, 5 equals 4 plus 2. Is this an equation? Well, the answer is yes. Of course it is. And the reason it's an equation is because we have an expression on this side, we have an expression on this side, and they're being connected by an equal sign. Boom. That's all we need. It's an equation. All right. We really don't care what this side is and what this side is. We just care that they're there and that we have an equal sign. So that is an equation. All right. But if we kind of look at this and try to simplify the expressions a little bit on the left and right sides, we'll notice that it just doesn't quite make a whole lot of sense. So if we simplify this, we're going to have 5 equals, what is 4 plus 2? Well, 4 plus 2 is 6, right? So 5 equals 6 would be another way to write this equation. All right. Now, the question then that kind of jumps at us is, how can this be? 5 does not equal 6. They are not the same thing. And equality seems to imply that they should be the same thing. All right. In this case, they're not. So it is still an equation. However, this would be an example of what we call a false equation. A false one. All right. It is not true. All right. We're expressing two things that are not equal to each other. So it is a false equation. All right. Let's go to this one over here. So that's one kind of equation that we can have, a false equation. Let's try this one. So here, again, we have two expressions, one on the left, one on the right. They're connected with an equal sign. Is it an equation? Yes, it is. Is it a false equation? Well, let's find out. So if we have a 6 on this side equals, now what's 4 plus 1 plus 1? Well, that's 6. And if we look at that, 6 does in fact equal 6. They are equivalent. So this would be what we call, and let's actually go in green here. This is going to be a true equation. Okay? A true equation. Yay. That's the kind we like. A true equation. Those are the ones that we look at and we go, yeah, that makes sense. 6 does equal 6. They are the same. So that is a true equation. Okay? Now, let's take it one step further. Let's start adding some variables. So let's look at this middle equation. What can we end up with here? Well, 4 plus x. We don't know what x is. X could be anything, and I'm not going to tell you what it is. All right? So it's a mystery. It's an unknown. We don't know what the x is. So you might be tempted right off the bat to say, well, then we don't know if this is a true or a false equation, because you're not telling me what x is. But let's just examine this a little bit closer. If we take this left side of the equation and just try to simplify it as much as possible, we're going to have a 4 plus x. There's nothing we can do. There's no like terms. There's nothing else we can do. That's it. So on the right side, however, we can do a little simplification here. We can see that x does not have a like term, but we do have a plus 2 and a plus 2. Those two we can combine. And when we combine them, they end up being plus 4. All right. Now this is very interesting. Why? Well, look at it closely. What's happening here? We're saying 4 plus x is equal to x plus 4. And if you think about that, doesn't that mean this is a true equation? 4 plus x equals x plus 4. Even though I don't know what the x is, it could be anything, but it doesn't matter. No matter what I plug in for that x, let's just say for the sake of the argument, I'm guessing that the x is a 2. Well, if x equals 2, then this would become 4 plus 2 equals 2 plus 4. 2 plus 4, which is in fact a 6 equaling a 6, right? And that would be a true equation. On the other hand, pick a number. What's your favorite number? What other number should we put in for x? Pick your favorite number. I'm going to pick, let's pick a 7. Okay, 4 plus 7 equals 7 plus 4. Well, 4 plus 7 is 11. 7 plus 4 is 11. This is a true equation. 11 does in fact equal 11. And this would be true for any number that you plug in for the x. No matter what that value is, you'll always end up with a true equation. Okay, for this particular one. So this is another example of a true equation because it's always true. No matter what we plug in for x, it's always true. Okay? Even though we have variables. Now, let's go to the next equation here. This one is x minus 3 equals 5. Looks pretty harmless there, but let's think about this one. We don't know what x is, and there's nothing on this left side that we can simplify. On the right side, we just have a 5. So obviously, nothing to simplify there. So the question becomes, is this a true or a false equation? And that's going to depend, right? Because in this particular case, unlike the last one, if I just pick a number, any number I want, and just guess that that's what the x is, because I haven't been told what x is, I'm going to guess that the x is a 4. All right. So if I plug in a 4 for the x, minus 3 equals 5. 4 minus 3, well, that's a 1. And does 1 equal 5? No. So this would be a false equation, right? Let's try another number, though. What if we plug in an 8? So if I say that x is equal to an 8, then I'd have 8 minus 3 equals 5. And 8 minus 3 is, in fact, 5. And 5 does, in fact, equal 5. So this is a true equation. Yay. All right. So for the same equation, we showed an example of it being a false equation and another example of it being a true equation. The only difference was what value we decided to plug in for x. All right. So this is really in and of itself neither a true or a false equation. It could be either. All right. So we have a special name for this. These ones we call a conditional equation. Okay. So conditional equations, they depend on whether or not they're true on the x, depending upon the x, the value that we give the x. So they're conditioned on the x. Conditional means it depends on what the x value is. So if the x value is, in this case, an 8, well then yes, this is a true equation. If the x is something like a 4, well, then it's not a true equation. It's a false equation. And I could continue plugging in all kinds of values for this x, hoping to find another true equation, or maybe just trying to find other false equations. I mean, there would be so many things I could plug in here that would give me false equations. Okay? So the point, though, is it depends. Whether or not this is true is conditional on what the value of x is. All right? So hopefully that makes sense. Now, let's move on. Oh, and actually, before we move on, just real quick. So there are 3 things that can happen. We can either get a false equation, a true equation, or a conditional equation. So keep those ideas in your head. All right, so moving on, we're going to talk about conditional equations, because as you'll see in future lessons this year, the one equation that we're the most interested in is the conditional equation. Because the true ones, they're great. They're always true. That's kind of trivial. There's not anything really interesting going on with those. The false ones, well, they're always false, and there's no point in working with false equations. They don't make any sense. So those aren't very interesting either. So what we are interested in are the conditional equations. And you'll find much of algebra is spent trying to figure out what values for x will make the equation, the conditional equation, a true equation. That's really what we're trying to do. We're trying to take a conditional equation and we're trying to decide what values for x will make this conditional equation true. That's what we're interested in. All right? So let's think about this for a second. If I've got an equation such as 6 plus x equals 11, what I want us to find is the solution for x. That's what I'm interested in. I'm interested in what makes this equation true. What value of x makes this equation true. And I give that value a special name. I might call it a solution. So if we find a value that works, we're going to call that the solution to this equation. Another name, which maybe doesn't quite sound as common to you or as familiar, is the name root. Okay, so you might also say that a number that satisfies this equation and makes it true is called the root of the equation. So root and solution, you can use them back and forth interchangeably. They both mean the same thing when we're talking about equations. All right, so 6 plus x equals 11. Just in your head, try to figure out what x would have to be in order for this to be a true equation. And hopefully you didn't have to spend much time on that. It should be a 5, right? 6 plus 5 is equal to 11. So 5 has to be the solution. We're going to say solution or the root, whichever one you want to call it. 5 is the solution or the root, which means that if we plug 5 in for this x, this equation will be, in fact, true, which is what we're looking for. All right? Okay, so let's take a couple of equations here, and what we're going to be primarily focused on is just being able to discern whether or not a particular number, a particular given number, is a solution for a particular equation. At this point, we're not really going to be solving equations yet. That will be coming very soon. But right now, let's just get some practice in making sure that we see why a number would be a root or a solution for an equation. So here, we have the equation x squared equals negative 3x minus 2. And the question is negative 2 or 1 a root? And then they also ask, how about a negative 1? Okay, so we're looking at those three possibilities, a negative 2, a 1, or a negative 1. Are any one of those a root for this equation? And to answer that, all we need to do is take each one individually and plug it into the equation and see if we end up with a true equation. So x squared, plug in the negative 2 for all of the x's in this equation. So negative 2 squared, right? Remember, when we plug in values, we like to keep them in parentheses. So this x, we're going to put a set of parentheses around that x and then put our negative 2 inside. Okay, so we have a negative 2 raised to the second power equals, now we have a negative 3, and then we have another x. So we're going to add another set of parentheses. What is the x? Well, we're saying in this case, for this first problem, we're going to say it's a negative 2. Okay, and then we have our minus 2. So what happens? Well, negative 2 raised to the second power is going to be a positive 4 equals negative 3 times a negative 2 is what? Positive 6, right? And then a positive 6, well, maybe we'll write that. Positive 6 minus 2. So we end up with a 4 equals 6 minus 2 is a 4, right? So 4 does equal 4. That makes sense. This is a true statement. 4 equals 4. Therefore, negative 2 is a root. It is a root or a solution for this equation. All right? So that's the negative 2. Let's try the positive 1. So if we plug in the 1 for all of our x's, we're going to end up with a 1 squared equals a negative 3 times our 1 minus 2, right? So 1 squared is going to be a 1. And then on this side, we have a negative 3 times a 1, which is a negative 3, minus 2. And now we're going to rewrite it here. 1 equals negative 3 plus a negative 2 is a negative 5. So here we've figured out the value for the expression on the right side and on the left side of the equation, and we end up with 1 equals negative 5, which is not true. That's a false equation, right? That's a false statement. 1 does not equal negative 5. So therefore, 1 is not a root for this particular equation. All right? How about a negative 1? Well, let's try that one. So if we plug in a negative 1, we're going to have a negative 1 squared equals negative 3 times a negative 1 times a negative 1 minus 2, right? So negative 1 squared, well, that's going to give us a 1. Negative 3 times a negative 1, it's a negative times a negative, so that's a positive 3. And then we have this minus 2. And then if we rewrite, 1 equals 3 minus 2, which is a 1, and 1 does in fact equal 1. So another solution, another root for this equation is going to be a negative 1. So these two would be the solutions or the roots for this particular equation. And there may be more, but we're only going to try those three options. That's all that we were worried about or concerned with, were the negative 1 and the 1 and the negative 2. So there may be more solutions to this equation, but right now we just know that there is a negative 2 and a negative 1. Both of those will satisfy this equation and make it a true equation. All right? So hopefully that kind of makes sense. Let's go ahead and try this one. I want you to try this one on a separate sheet of paper. It's just a very similar thing. If we have x squared plus 7x equals 10, is negative 2 or negative 5 a root? So go ahead and pause the video and give it a whirl and see if you can decide. Okay, so hopefully you didn't have too much trouble with this, but let's go ahead and do it together. So how are we going to do it? Well, we're going to just simply start by trying out the negative 2. We're going to say, let's just assume negative 2 works and see if we end up with a true equation. So if we plug that in, this again, we're going to think of putting this variable in parentheses, and we can put this variable in parentheses. So we have an x. Inside that, we're going to have a negative 2 now instead of an x. That's going to be raised to the second power plus 7 times our negative 2 equals a 10. Now, let's take one side at a time. Negative 2 raised to the second power, that's going to be a 4, plus 7 times a negative 2 is going to be a negative 14. I'm just going to put that in parentheses because I don't like having plus minus signs right next to each other. Equals, on the right side here, there's nothing we can do. It's already as reduced as possible, or as simplified as possible. So now we can add this side up. 4 plus a negative 14, well, that's going to give us a negative 10. And we still have this 10 on the right side. So we end up with negative 10 equals 10. All right? Is that true? Well, the answer is no. That's not true. Negative 10 does not equal negative 10. So negative 2 cannot be a root for this equation. All right. Let's try the next number. So now we're going to try the negative 5. So we plug that in. We have a negative 5. That's being raised to the second power plus 7 times our negative 5 equals 10. All right. Now, I'm going to give myself a little more room here. Now, let's go ahead and work this out. And I should probably add at this point, this might be a good place to talk about this. When we solve these equations, or when we simplify these equations, each time we do them, it's good to keep our equal signs right below each other. You want to stay organized, otherwise things will really start getting sloppy in the future. So keep the equal signs right on top of each other. Take each side at a time and simplify them as much as possible. So here we can say this 10 is still going to remain a 10. We'll just bring that right down. Now simplifying this side, we could say that negative 5 raised to the second power is a 25, positive 25. And then a positive 7 times a negative 5 is going to be a negative 35. Okay? And now we're going to go down one more level here. Put our equal sign against. They're nice and straight in line with each other. This side doesn't change. This is still a 10. This side now we have a 25 minus a 35, which is what? Negative 10. Right? So, is this a root? Well, does negative 10 equal 10? No. So in fact, neither of these are roots. This negative 10 does not equal 10. So this is not a root as well. All right, so hopefully you can see that neither one of these gave a true equation. So in this case, neither one of the options is going to be a root or a solution to the equation. All right, so let's just try one more problem, and then we will call it good for the day. So let's take, let's see here. What if we go x squared equals negative 5x minus 6. All right, and the possible solutions that I want you to try are negative 2 and a positive 5. All right, so which one of those, if either, would provide a root for this equation? So go ahead and try this on a separate sheet, and then we'll work it out together. All right, so let's plug each in individually. So if we have our negative 2, we have a negative 2 raised to the second power equals a negative 5 times a negative 2 minus 6. All right, negative 2 raised to the second is going to be a 4. Negative 5 times a negative 2 is going to be a positive 10. 10 minus 6 is 4. Bingo! There we have it. So negative 2 is a solution. It is a root for this equation. All right. Next, let's try the positive 5, because that very well also could be a root. So if we have 5, we'd plug that in and have 5 squared equals negative 5 times a 5 minus a 6. So 5 squared, well, that's going to give us a 25. We'll keep our equal signs on top of each other here. Minus 5 times a positive 5 is a negative 25. Negative 25 and a minus 6 is going to be a negative 31. So this does not equal each other. So this would not be a true equation. And therefore, we can say positive 5 is not a solution. Okay, so negative 2 is, positive 5 is not. So hopefully that kind of makes sense to you, Luke. It's kind of fun going through these and testing them out and seeing which ones are going to be the roots and which ones aren't. In future lessons, we're going to start talking about how to solve these without being given a couple of options to try. All right, so go ahead and good luck on your homework with this, and we will see you in the next lesson.